Today we explore the Hopfield network, a neural architecture that bridges physics and computation through the elegant mathematics of associative memory. This isn't merely another neural network, it's a system that earned John Hopfield the 2024 Nobel Prize in Physics and fundamentally connects to modern transformer architecture through self-attention mechanism, which is demonstrated through the 2020 paper Hopfield network is all you need. Unlike traditional fit-for-work network, Hopfield network operates as recurrent adjunctor network, where every neuron connects to every other neuron, creating a fully connected system that can store and retrieve patterns through energy minimization. The mathematical elegance emerged from two core principles. First, the free energy principle. Biological systems minimize the difference between predicted and actual sensory input. This manifests as KL divergence minimization between the system's internal model and environmental reality. Second, Hebbian learning governs synaptic plasticity through the principle neurons that fire together wire together. The way update rule follow delta W equal eta times x times y, where eta represents learning rate and sy denote pre and post synaptic activity.
Let's dive into the original process. Suppose we have n, in this case, it should be 3 square images. To use it with the classic Hopfield network, we first convert the images to black and white, producing polybinary values of -1 or +1. Next, we flatten the image matrix into a d-square size vector, where d is the edge of each image. We will then initialize a weight matrix, which will be denoted as W, constructed as the sum of the outer products of each vector with itself. Next, we let S represent any one of the images stored in W that has been noisified. As before, S is converted to polybinary values and flattened into a d-square size vector. In the synchronous mode, we update all neuron states at once via this function, where sign u would take the sign of each element of the vector. The process will continue until the new state is equal to the previous state. By contrast, the classic Hopfield model often favors a synchronous update, using the same sign function, but with each component of S changes simultaneously, which guarantee the energy monotonically decreases and the system settles reliably into a single attractor. Convergence occurs when the energy function, which is being shown on the screen, approaches its minima. What's with the energy function, you may ask? Now, picture the energy function as a 3D hilly landscape, where each valley is one of our store patterns. We place a ball at the coordinates given by our initial state S. With each asynchronous update, the ball rolls a little further downhill, always seeking lower energy. Bit by bit, it loses height until it finally settles in the nearest valley, retrieving the correct memory. However, when under certain conditions, the Hopfield network can settle into a spurious attractor, a state that isn't one of our originals, but rather a mix. In our landscape, these appear as small, unintended dents between the main valleys. If you drop the ball there, it will come to rest in the wrong basin, and you'll retrieve a hybrid pattern instead of a true memory. Now let's compare our two classic Hopfield versions side by side. In the sync version, the pattern is retrieved faster, but it sacrifices accuracy. On the other hand, the bar of the sync version is more smooth and consistent. Now let's turn to the discrete modern Hopfield network, which still operates on polar binary vectors but dramatically lifts the classic capacity limit. The fx function in the energy function is equivalent to x to the power of alpha, with alpha a tunable exponent. But later, an even cleaner special case was proposed, set fx is equal to e to the power of x. Plugging that into the discrete modern Hopfield energy functions gives the energy function, which being shown on the screen. The retrieval steps then reduces to an attention style update, compute similarities. But why this energy function, you may ask? We can see on the screen fx is equal to minus the energy function, which means minimizing E is maximizing F. We then set SL to the direction of F. This rule ensures F never decreases, with each bit flipped. Consequently, only the store patterns where F is maximal or E minimal remain as stable attractors. Although the discrete modern Hopfield network overcomes the classic limits on capacity, spurious convergence, and scaling, it still requires binary inputs. To extend these same attractors dynamics to real-valued data, we now turn to continuous Hopfield network. The energy function now becomes the one on the screen. To efficiently minimize our continuous Hopfield energy, we apply the concave convex procedure, or CCCB for short. We split the energy function into two parts, with E1 is a convex and E2 is a concave. When applying CCCP, we get this function for updating S. We then obtain the elegant attention style update. What's special about this update step is that each iteration is guaranteed to decrease E, and when S is already close to a store pattern, a single CCCP step perfectly converges to the attractor.
We will look at how a Hopfield network can be used to solve the N-Queens problem. The idea follows the approach proposed by Yasif Manjuk in his 1995 paper called Solving the N-Queens Problem with a Binary Hopfield Type Network. The task is to place N-Queens on an n-by-n chessboard in such a way that no two queens can attack each other. To make the Hopfield model work for this problem, a few key changes are made. First, the model is completely binary. Each neuron can only take a value of 1 or 0, indicating whether there's a queen in that position. Second, the network can start from a random state and still converge to a solution. And finally, the energy function is specially designed so that its minimum corresponds to a valid solution. So instead of learning and recording patterns, the network is used here as a search algorithm. Its goal is to find a state that minimizes the energy. The core of this method is the energy function, which you can see here. The original form of the function is actually more complex, but its purpose is straightforward. The energy function is designed so that any violation of the N-Queens rules increases the energy value. This energy function includes three main penalty terms. Let's bring it down. The first term, with parameter A, penalizes having more than one queen in any row or column. The second term, with parameter B, analyzes queens on the same diagonal, and the third term with parameter c ensures the total number of queens on the board is exactly n. The sigma parameter provides a little flexibility, allowing the network to temporarily explore states with slightly different number of queens, which can help it escape local minima. Now, let's talk about how the network actually evolves over time. At each step, the network computes the input potential for each neuron ij, called Uij, based on the negative partial derivative of the energy function. This tells us how much that neuron's current state affects the total energy. Then, we apply a binary threshold function. If the potential is negative, the neuron is set to 0, otherwise set to 1. This update process is repeated over multiple steps. We conducted experiments with 4, 8, and 16 queens using 3 initialization strategies: all zeros, all ones, and random values. For each setup, we ran the network 100 times to measure its convergence rates. With the original paper's parameters, the network achieved near perfect convergence, often 100%, regardless of the initial state. Interestingly, when we relaxed the diagonal constraint in asynchronous mode, the model still performed very well. But in synchronous mode, when we force the network to place exactly n queens, the success rate drops significantly. This highlights how sensitive the model can be to its parameters. To sum up, this Hopfield network model is a powerful approach for solving the n-queens problem. It offers a high convergence rate and strong stability, even with random initial states. However, these trains come with challenges. The energy function is really complex, and fine-tuning the parameters requires a lot of time and careful experimentation.
Welcome. In this section, I'll explore an unconventional approach to solving Wordle using Hopfield networks, inspired by how our brains actually process partial words. When you see detail in your mind, your brain doesn't randomly guess. It systematically explores possibilities like deity, dirty, dusty, each triggered by spreading activation through your memory network. While existing Wordle solvers have achieved less than 3.4 turns to complete on average using information theory or reinforcement learning, they lack biological plausibility. They rely on computationally intensive optimization and perfect knowledge of word frequencies, something humans don't have access to. So I think Hopfield network is fitting for this task based on its spell plausibility. However, classical Hopfield networks have severe limitations. They can only store about 0.14 n patterns reliably, and they suffer from spurious attachments and similar patterns interfere with each other. Modern Hopfield networks solve these problems through a key innovation, replacing the quadratic energy functions with exponential interaction functions. And after applying the concave convex procedure optimization for the energy function, the update rule becomes mathematically equivalent to transformer self-attention. Instead of the classical binary state, we now have continuous dynamics with exponential storage capacity and is able to pull apart closed patterns. Here's how I implemented the Wordle solver. I encoded 5-letter words into 130-dimensional vectors using one-hot encoding, 5 position times 36 letters. The core architecture used modern Hopfield dynamics with softmax attention to retrieve stored word patterns from the flattened vector. When given a partial word, the network computes the similarity between the partial pattern and all stored memory, applies softmax attention weights, and retrieves the most similar complete word through winner-take-all decoding. To handle multiple paired retrieval, I implemented what I call a suppression mechanism. After retrieving a word, I remove that pattern from memory to force the network to suggest different alternatives. Finally, I use Lorentz approximation to select the best candidate from retrieved words by finding the dominant eigenvector of the word similarity matrix and choosing the word with a small angle to this direction. As a great idea as it seems, unfortunately, this approach failed. It taught me crucial lessons about research and biological inspiration. The biggest insight: biological inspiration doesn't automatically translate to good algorithms. Just because the brain does something doesn't mean copying that mechanism will work in silicon. The gap between cognitive plausibility and computational efficiency is enormous. If I were to attempt this again, I would formulate it as constraint-aware optimization rather than pure pattern completion. The energy function would include explicit penalty terms for violating green, yellow, and black constraints, while still biasing towards true memory terms. Instead of memory deletion, I implement inhibitory fields to suppress repeated suggestion while preserving network stability. And rather than sparse one-hot encoding, I use dense distributed representations that capture semantic relationships between words. Sometimes the most valuable research is the kind that doesn't work because it teaches you why it doesn't work and what to try instead.